Okay, in this video we're going to go back to a little bit of multivariable calculus and talk about how vectors play a role in linear algebra. So a matrix with only one column is what we call a column vector, or just simply a vector. So we used to write vectors like this vector here, v, as the vector, a different color, 2, -3. Or we used to write w as 1, 5. But now we're putting them in columns so that we can manipulate these vectors with matrices and make them a part of our matrices. If we would like to do algebra with vectors, they need to be the same size. So just like we would if we wanted to add these two vectors together, they needed to have the same number of components. Same thing with these two vectors. And then we really just do algebra one component at a time. So let's take a few simple examples down here. Okay, I guess I'll do b. Okay, so 2 times u. That's the same as saying 2 times the vector 2, -7. Okay, and I'm just going to multiply every component by that constant, basically distributing that constant. So 4, -14. Not so bad. Okay, if I wanted to multiply and add together, so in this case I would have 2 times 2, -7 plus -3 times 1, 4. I definitely want to multiply first. So I get 4, -14 plus -3, -12, and then I add across, one component at a time. So the first component, or first entry, 1, second entry is -26. Hopefully that's right. Got my constants right. Okay, simple enough. Vector addition hasn't changed. We're just doing it in a new format, kind of. One reminder that two vectors are equal if and only if their corresponding entries are equal. Okay. So it's not just that they have the same numbers inside the vector, it has to be corresponding. So what does this look like in geometry? Or rather in a plane. So we still have 2 by 2 vectors, and these are in the set of all real points in the xy plane, R2. If we are adding two vectors, which I think you've seen, we add head to tail. So if I wanted to add this vector to this vector, their sum is the third vector that reaches from the origin out to that furthest point. And we make kind of a parallelogram, as it says here. One of the vertices is u plus v, and the other ones are 0, which is actually a vector itself. We call this the 0 vector. Okay, u, we didn't identify u or v here, but u and then maybe v. Remember that you can also add v and then u. As we'll see a little bit later, the algebra rules algebra rules still apply, so addition is still commutative. That's what I'm looking for. We've seen this diagram before. It should look very familiar. Pretty sure we saw it when we started parameterizing things in multivariable calculus. I'm sorry, I cannot speak this paper forward. There we go. So in 3 dimensions, same thing, but it's a 3 by 1 column matrix. Again, starting from the origin out to a certain point. But you can have, just as like we have infinite dimensions, we can have many dimensions, we can have as many entries in a column vector as we would like. It just changes our kind of representation of or graph of it. We're really not going to graph a lot in linear algebra, but just so you can get some visualizations, you'll see a little bit of it today. Again, 0 vector is a vector in which all the entries are 0. Notice that the 0 vector can be any size depending on what you need. So if I need a 0 vector in 2 dimensions, 0, 0. If I need it in 3 dimensions, 0, 0, 0. If I need it in 5 dimensions, here we go. Just depends on what we need, what kind of matrices we're dealing with. Okay, so just a little more vocab. All right. So here are our algebra properties, which should look relatively familiar if you have been through like Algebra 1. So just to go through and name them really quick, and so these are all for all vectors. Anything you see in bold here is a vector. Anything that is not bold is considered a scalar. So here, if I'm adding two vectors, I can add them in the other order. So we've got the commutative property. Here we've got the distributive property with constants. Here we have the associative property, okay, with vectors. Here we have the associative property with constants. Here is the additive identity. So adding the zero vector results in the same vector. Okay, I can also kind of factor out, I guess this is another kind of associative property with constants. Here we have the additive inverse. Okay, so u and negative u are opposites of each other, results in the zero vector. And here we have the multiplicative identity. Multiplying by a vector of all ones gives me the same vector. Okay, these are all the same kind of things you would expect from regular algebra. Now they just apply to vectors as well. And here's where we're getting into what we really want to talk about today. This will take us into 1.4 and 1.5, linear combinations. I can combine a lot of vectors into a kind of what we call a linear combination, meaning I'm not multiplying any vectors, not doing any weird operations to any of the vectors. I'm multiplying each vector maybe by a constant, and then adding all of those together. Sometimes you'll see that these constants are called weights. How much does each vector weight into this equation? But what this diagram is, I ask you to just pause here and kind of figure out a couple of these kind of connecting lines here. So let me use a different color other than blue. But what this diagram is showing you is many linear combinations of vector 1 and vector 2. So let's point out vector 1 first. Here is vector 1 labeled in your diagram. And here is vector 2. Okay? So you can see that if we follow along these lines, these are just scalar multiples of vector 2. So here's 2 vector 2, here's 3 vector 2. Over here we've got 2 vector 1, 3 vector 1. Okay? And also negative. So negative vector 2, negative 2 vector 2. If I do vector 1 minus vector 2, I get to this point over here, which is kind of a third vector you can see. I can also add multiples. So if I did vector 1 vector 2 and then minus 2 vector 1, I would get this over here. So back 2 vector 1 lengths, and to the right 1 vector 2 length, I would get to this point. So what we're trying to show you here is that the entire plane almost could be made up of a linear combination of vector 1 and vector 2. Okay, so I can get to a lot of points by either multiplying by constants and adding or subtracting two vectors. That will become important in a second. But let's just get some practice expressing things as linear combinations first. So I have 4 vectors here, and they've given me, I guess you can't really tell the difference between red and pink. I think that was a bad choice. I apologize. So let's see. Excuse me. 2, 1 is this vector here, which I'll stay in pink. And I'll change vector 2, negative 2, 2 to be here. So hopefully that's visible. Okay. When we make, if we ask if A is a linear combination of V1 and V2, that means could we graph A on here by somehow multiplying and adding together these two vectors? I think it's easier to think about it numerically than it is to think about it graphically. So what we want to do is we want to see if we can add vector 1 and vector 2 together somehow to get 0, 3. Okay, so if I take a look really quick, I know if I just add vector 1 to vector 2, I will get 0 as the top component. And if I add the second components, 1 plus 2, I will get 3. So vector A is really just the combination of V1 plus V2. Easy enough. Vector. Okay, so if we look at finding a linear combination for B, I want to think about combining the two components again. So I see that I need to get negative 4 as my answer. So if I multiply this by negative 1 and add it to this, I will get negative 4. Let's check the other one. If I multiply negative 1, I get negative 1 plus 2 is 1. Great. B is a combination of negative 1 vector 1 plus vector 2. And I'm going to skip C, but I want to talk about D really quick. And C will be filled in on the notes if you want to check your work later. So if I look at D, I notice that I'm supposed to get 7 and -4, which seems relatively difficult given that I'm only given even components for the first two. So how else could I write this? So I'm going to go ahead and give us a general equation, a linear combination. So we're going to say that vector D is equal to C1, which will be some constant, 2, 1, plus C2, -2, 2. And I could have used also the variable x, and I just wanted to use C really quick. So what does this look like if we multiply that in there? Remember, these are kind of weights or constants. So this will be 2C1 plus, or excuse me, the second component, 1C1 plus -2C2 and 2C2. And based on vector addition, all I have to do is add across. So that would be 2C1 minus 2C2. Okay? And 1C1 plus 2C2. That's the vector I'm looking for to be equal to D, 7, -4. So I've kind of just created a system of equations that is perfectly solvable here. So if I kind of write this out to the side, I would get 2C1 minus 2C2 equals 7, and 1C1 plus 2C2 equals -4. Okay, if I add those together, okay, I will get 3C1 equals 3. So C1 will equal 1. If I plug that back into either one of my equations, I'll just use the second one, I get that 1 plus 2C2 equals -4. Okay, so I have to subtract, so I get 2C2 equals -5, C2 equals -5 halves. Okay, so if we rethink about this, our linear combination will be, and actually I'll write it using vector names instead of the actual vectors themselves. But remember, you can write it either way. So C1 was 1, so that means I have 1 V1, and then minus 5 halves V2. So finding linear combinations is the same as solving a system of equations, which is where we're going to get into using a matrix for this kind of thing. Okay, so I'm going to skip example 3 because I think it's a bit trivial, but you should practice it just to make sure you've got this. But let's take a look at example number 4. I want to write a vector equation that is equivalent to this system of equations. So if I write each as their own vector, okay, I can kind of use the x1s not as the components, but the x1s as the multiples. So this is, or excuse me, the constants or weights is what I'm looking at, things I'm multiplying by. So x1, the components would be 4, 1, 8, and x2 would be 1, -7, 6, and x3 would be 3, -2, 5. And this should all be equal to 9 to 15. But this should look relatively familiar because I was able to rewrite this in a different way last class. So if I can also rewrite this as an augmented matrix. So 4, 1, 8, 1, -7, 6, 3, -2, 5, and 9, 2, 5. And then I can check to see whether or not this matrix has a solution and is consistent, so that this system will have a solution. So our connection I'm trying to draw out here is that a vector equation, a linear combination of vectors, has the same solution set as the augmented matrix. So this system here will have the same solution, x1, x2, x3, as if I had found the solution using the augmented matrix method. Okay? And in particular, a vector b can be generated by a linear combination of these vectors if and only if there exists a solution to this. So this is kind of where we start using the matrix methodology to check whether or not a vector is a linear combination of other vectors. Okay, so just to set up example 5, because I don't want to take my time in the video going through row operations, but let's just set this up. Is B a linear combination of A1, A2, and A3? Okay, that means I am going to put each of these as my columns and see if I can do row reductions to get a solution. But I should write down the right components. 2, 0, 5, 5, 2, 0, 8, and negative 5, 11, negative 7. Okay, and remember, you are doing row operations. Your methodology here is to use this as a pivot and get all zeros underneath that, and then move down and to the right. Remember to check if at any point you get something, a line that does not make any sense, like 0, 0, 0 equals a number, you know that the system is inconsistent, which would mean that B is not a linear combination of these 3 columns, vectors. Okay. You want to check yourself, go ahead and pause here, and it'll be filled in on the filled notes. Okay, here's a second example. All right, already given. This is what we would think of as the coefficient matrix now, and you would just put B in as the augmented part and see if it is consistent. Okay, one other definition I want to talk about is that if we say that a vector can be a linear combination of other vectors, then we say that that vector is in the span of these vectors. Okay, so we have several sets of vectors, some real number, okay, and they're in some dimensional, nth dimensional space. Then the set of all the linear combinations of those vectors can be denoted by the span of those vectors. Okay, so that means if a vector is in a linear combination of v1 through v whatever, it's in the span. Okay, so again, this statement here, asking whether vector b is in the span amounts to whether asking whether the vector equation has a solution, or whether the linear system with this augmented matrix has a solution. Okay, that span contains every scalar multiple of the vectors that are in there. I think this was to say v1 through vp. Okay, so if it's every scalar multiple, what vector must always be in that span? Well, think about 0 is a scalar, so the 0 vector is always in the span. And remember, the 0 vector, excuse me, the 0 vector can have any amount of components, but all of them are 0. So it doesn't matter what size these vectors are. The 0 vector is always in the span of those vectors. Sometimes we call that the trivial solution, but it counts. Okay. All right, last couple things. If I want the span of one vector, that just means it's all the scalar multiples of that vector, including the vector 0. So all points on the line, on this line that goes through that vector, and the origin. Okay, so you can see that v itself, you can squint a little bit, but v itself is the orange one that's in here, 2v is this green one, 1.5v is a blue one, they all lie on the same line. Okay. If I want the span of 2 vectors, then I'm talking not only about a line in this direction, but a line in this direction, and any, excuse me, linear combination of them. So I'm really talking about a plane. Okay, so the span of 2 vectors is a plane in 3 dimensions. Okay, it contains the 2 lines through u, v, and the origin. Okay, 0. Okay. So I've left a couple of practice problems at the back for you to try, especially since I know that not a lot of you are going to try the homework. But they will be filled in on the field notes, so you have the answers. Okay? All right, so for example 7, I'm going to ask for what values of h, which is here, is y in the plane generated by this. Again, I'm asking you find an h value such that this vector will be in the span of these two vectors. Another way of asking that would be find an h value such that this vector is a linear combination of these vectors. And you can use a matrix to do that, or you can try just doing straight up multiplication. Okay. Again, here's another vector that has 3 columns. So I've got 3 column vectors that I'm looking at the span of here. And B is this vector. Okay, so W is the span, or the set of all linear combinations of the columns of A. Is B in W? Is B in the span of this vector set? And you can find that using the augmented matrix. Okay, we also want to show that the third column of A, so this one, is in W. What that means is you can, instead of using B as part of the augmented matrix, you can again use this column as part of the augmented matrix and see if it has a system. Note that it should be in W because W is the span of these 3 vectors. That includes every scalar multiple of these 3 vectors, including 1 times this vector. So we're really just proving that this vector, 6, 5, 1, is in the span of these 3 vectors using our matrix row reduction. Okay, there'll be another video for 1.4 and 1.5, which will deal more with these linear combinations and the span of several vectors.